So far, we've covered quite a bit to get you started. We added a new machine and material to the iMachining database. We defined the CAM part, as well as the rough and finish machining of the outside contour. I talked about the iMachining Technology Wizard in depth, and we even experimented with some of the different settings. I also showed a case where you would need to use the iRest technology type prior to iFinish. In this particular video, I want to talk specifically about the tool definition and its important parameters that are related to iMachining. You'll also see how the wizard calculates the depths and what the importance of ACPs are when machining. These somewhat interrelated topics will be covered in 4 operations. This will be the last part in this series, so let's finish up. So to pick up where we left off, let's first discuss the tool definition and what parameters you should be aware of when using iMachining. I want you to open up the last roughing operation that we defined, iRough Contour 1. Then switch to the Tool page and click the Select button to display the Part Tool table. So here we have our tool that we chose for this iRough operation. On the Topology tab, I want to mention that there are 3 parameters that will have an effect on the cutting conditions in which the wizard outputs. As you may have guessed, the tool diameter is the first and one of the most important parameters. This tool was defined to have a 9.5 millimeter diameter. Make a mental note of that as we go through this video. The second parameter that is important is the cutting length. If you remember, we just used the default value, which gave us a cutting length of 24 millimeters. The wizard uses the cutting length to calculate if multiple steps are needed to achieve the pocket depth. Setting the number of flutes is also important. The correct number of flutes will assure the proper chip size is given to each flute. Changing this value will also change the cutting conditions, usually just the feed. Note that the tool we're using has 4 flutes. Let's now switch to the iData tab. Here we can define parameters that are more specific to the iMachining technology. The material database will be automatically selected based on the CAM part default, which if you remember we selected when we added our first iMachining operation for this exercise. Now, I should mention that it is possible to choose a different work material for each of your tools. I use this when machining different materials in one CAM project, like in the instance I have a fixture or something. Let's now talk about the tool material. This adjusts the cutting speed for a given type of material from which the tool is made. The default is set to carbide at 100%. By selecting a different tool material from the drop-down list, a percentage adjustment will be used to calculate the maximum cutting speed. Take note that an override checkbox is provided, so a percentage adjustment can be set manually as well. For this example, let's just keep the default option of carbide at 100% for our tool material. If we set a machining level for the tool, the wizard will position the slider at this level when choosing this tool from the Part Tool table. How about we set the default level to 5 for this example? And last but not least, setting the helical angle is important for calculating depths based on axial contact points, or ACPs, which we'll cover in more detail as we continue through the rest of this video. There are 5 typical end mill angles to choose from, or we may also manually enter a value. For this example, we'll just use the default 45 degrees for the helical angle parameter. Clicking the Select button will confirm the tool definition, choose the tool for the operation, and finally exit the Part Tool table. If we switch to the Levels page, we'll see that the pocket depth is an even 15 millimeters. Keep this value in mind, and then switch to the Technology Wizard page. You'll see that the machining level for this operation is now set to 5 on the slider, so we'll be machining a little less aggressive than before. Now, we'll sort of dissect how the wizard is calculating the depths based on the tool information. Looking at the step-down output grid, we can see the wizard calculated one step at 15 millimeters to give us the full pocket depth. Notice that the ACP value is set to 2.0 and the depth is painted green. Now I'm going to switch to a fully modeled end mill to show you where the 2 ACPs come from. Here is the tool with a depth of 15 millimeters. Now, let me show you a sectional view of the tool's contact area. Not counting the bottom point of the end mill, we can see that there are 2 contact points lined up vertically. This is where the 2 ACPs come from. I'll now switch back to our CAM project. The wizard giving us a green color for this depth in the step-down output grid indicates that this is a good situation for stability, meaning it is highly unlikely that vibrations will develop. Let's click Save and Calculate to calculate the operation once again, this time with the changes in the tool information and machining level aggressiveness. Let's also simulate the new results by clicking Simulate. Let's use the Solid Verify mode this time. Switch to the Solid Verify tab and then click the Play button. The tool performs the pocket roughing toolpath at the full pocket depth, and based on the ACP indication, we really have no need to worry about the stability of this operation. Go ahead and exit the Simulation Control Panel. Now, of course, it is up to you to make sure that your machine and setup are determined rigid enough. If they are not, then vibrations could still develop. But like I mentioned earlier, this is one of the roles of the machining level slider. It provides easy control over the aggressiveness, as well as safe sets of cutting conditions. I also want to mention that the ACP indication by itself has no effect on the cutting conditions, but it should still be used as a guide. Achieving good ACPs can definitely help you to avoid potential vibrations. How about we look at a few examples where the ACP indication is showing us depths painted something other than green. First, go ahead and close this iMachining operation by clicking Exit. Next, we're going to define only the rough machining of these 2 elevated surfaces and the pocket ledge to see how the depths are calculated and what the wizard is indicating for ACPs. But before we do that, what do we see here in the InventorCAM Manager? Well, since we recalculated the Irf operation, the latter IRest operation is no longer calculated. And as we know, that's a pretty quick and easy fix. Like we did previously, in this instance we can simply right-click the IRest operation and choose the Calculate command to recalculate it. Now, let's define an Irf operation to machine this elevated surface along the pocket wall. In the InventorCAM Manager, right-click Operations, Add Milling Operation, 2D iMachining. On the Geometry page, click the New button. For this operation, the geometry is defined as a semi-open pocket. In the Graphics window, pick on the edge of the elevated area to start the chain selection. Use Auto Constant Z to close the chain, and then click Yes to accept the chain selection. Now, we have to inform the iMachining technology what edges are open. So right-click Chain 1 in the chain list and choose Mark Open Edges. When the Mark Open Edges dialog box appears, let's use the From To Entities option to simplify our selections. Following the chain direction, pick on the first entity and then the last entity to mark them and the ones in between as open. Click OK to accept, and then click Finish to confirm the geometry selection. Moving down to the tool page, let's choose our 9.5mm tool from the Part Tool table. Then, let's switch to the Levels page to define the milling levels for the operation. We'll pick the upper level first, which is the top face of our stock model. Then we can pick the pocket depth, which is the top of the elevated surface. Now we can switch to the Technology Wizard page to see how the wizard is calculating the depths. Looking at the step-down output grid again, we can see the wizard calculated one step at 14 millimeters to give us the full pocket depth. You'll notice now that the ACP value is set to 1.9 and the depth is still painted green. Let's look at another model. This one showing the 14 millimeter depth to see how the flutes line up vertically. Well, we can see that there is one contact point above the bottom of the end mill and 0.9 of the next. Now, although the depth did not give us a perfect 2 ACPs like we had before, there is a 20% tolerance on any ACP over 1. In switching back to our CAM project, the wizard is telling us that 0.9 of the next ACP is within the 20% tolerance, and the depth gets painted green for good stability. Let's click Save and Calculate to add this Irf Operation to the CAM tree and to calculate the iMachining toolpath. Now, let's define an Irf Operation to machine the other elevated surface. First, click Exit to close this iMachining Operation dialog box. Then, in the InventorCAM Manager, right-click Operations, Add Milling Operation, 2D iMachining. On the Geometry page, click the New button to define the machining geometry. For this operation, the geometry is defined as an open pocket. Pick an initial edge on the island, use AutoConstant Z to close the chain, and then click Yes to accept the chain selection. In the chain list, right-click Chain 1 and choose Mark Chain as Open. Now we can click Finish to confirm the geometry definition. Next up, let's move down to the Tool page and choose the tool for the operation. We'll use the same tool that we used previously. Next, we'll switch to the Levels page to pick our milling levels directly off the model. First is the upper level, which is again the top face of the stock model. Then we can define the pocket depth, which is the top of this elevated surface. Now we can switch to the Technology Wizard page to see how the wizard is calculating the depths for this operation. Looking at the step-down output grid again, we can see the wizard calculated one step at 13 millimeters to give us the full pocket depth. You'll notice now that the ACP value is set to 1.7 and the depth is painted yellow. Let's look at another model. This one showing the same tool at a 13 millimeter depth to see how the flutes line up vertically. There is one contact point above the bottom of the end mill and 0.7 of the next. In switching back to our CAM project, the step-down row is painted yellow because there is at least one contact point above the bottom of the end mill. The wizard is indicating that the situation for stability is okay, but there is a medium likelihood that vibrations could develop. So what can we do to avoid potential vibrations in this case? Well, there are quite a few things we can do. We could try changing the tool or the step down to achieve a better ACP indication to help put us in the green, so to speak. We could also just reduce the machining level, which can help us avoid vibrations. So for this exercise, that's what we'll do. Since we're in the yellow, let's reduce the slider to 3. Now go ahead and click Save and Calculate to add this Irf Operation to the CAM tree and to calculate the iMachining toolpath. Let's now define one more Irf Operation to machine the pocket ledge and the top of the bosses. In the InventorCAM Manager, right-click Operations, Add Milling Operation, 2D iMachining. On the Geometry page, click the New button to define the machining geometry. For this operation, we can define the 2 inner islands as open first, and then the ledge can be defined as an open pocket with island. So in the Graphics window, pick on the 2 island contours. Since they are already closed, we can just click Yes to accept the chain selections. Next, we should pick on the outer edge of the pocket ledge, use Auto Constant Z to close the chain, and then click Yes to accept the chain selection. Then, select the inner chain in the same way. And finally, in the chain list, mark chains 1, 2, and 3 as open. We can now click Finish to confirm the geometry definition. Move down to the tool page and choose the same 9.5mm tool for this operation also. Next, we'll switch to the Levels page to again pick our milling levels directly off the model. First is the upper level, which is again the top face of our stock model. Then we can define the pocket depth, which is the lower face of the pocket ledge. Let's switch to the Technology Wizard page one more time to see how the wizard is calculating the depths for this operation. In looking at the step-down output grid again, we can see the wizard calculated one step at 5mm to give us the full pocket depth. Now, the ACP value is set to 0.7 and the depth is painted red. Let's look at one more model. This one showing the same tool, now at a 5mm depth, to see how the flutes line up vertically. There is no contact point above the bottom of the end mill. The 5mm depth is only 0.7 of the first contact point. In switching back to our CAM project, the step-down row is painted red to indicate that this is not a particularly good situation for stability, and there is a high likelihood that vibrations could develop. So for the purpose of this exercise, let's reduce the machining level slider again. This time we'll lower it all the way down to level 1. We can now click Save and Calculate to add this Irf Operation to the CAM tree and calculate the iMachining toolpath. Now, it's just not possible to always be machining with preferred ACPs, but by monitoring the ACP values and the cutting results, over time you may find that matching a tool to the current depth to get good ACPs is beneficial. Well, there you have it. The most common need-to-know topics about iMachining were covered in this Getting Started exercise. These topics included things like adding a new machine and material to the iMachining database, an in-depth look at the wizard, using the IRES technology type, and the tool definition in conjunction with ACPs. We got into some pretty heavy stuff about iMachining, so congratulations on successfully completing this second exercise. And thanks again for watching.